All right, we will pick up where we left off yesterday, doing our oxidation reduction. This one that we were doing would be extra credit for balancing it, but not extra credit for getting the oxidation numbers. All right, so not sure where that went, but anyway. Okay, right. All right, so we had our oxidation numbers. We had our reduction where Mn went from 7 to 2. We had our oxidation where Fe went from 2 to 3. So all of that is regular credit. The extra credit is going to be what is the electrons gained and lost. They have to be the same number. So how many electrons were transferred? So here we had to gain 5 electrons per Mn. And here we had to lose 1 electron per Fe. All right, and so our 5 electrons gained have to equal the 5 electrons lost. And so the lowest common multiple between 1 and 5 is 5. And so you have 5 electrons gained and 5 electrons lost. So to balance the reaction, you would have to put a 5 here and a 5 here. All right, and so then you could do the charge. On the test, it's not going to be about charge. On the test, I'm going to put the OH minus over here. Is that, well, let's see. Let's do that. So we'll do the charge. So here we have a -1 for our MnO4. We have a +10 for our 5 Fe plus 2s. And so that's a total of +9 on the left. On the right, we have 1 Mn plus 2. And we have 3 Fe plus 3, so that's +15. And so here we have a +17, and so those are not equal. All right, and so the OH minus is going to be on the right side, and we're going to need 8 of those. If we have 8 OH minuses, that means we have -8, and so that is then not +17 anymore. Now it is a +9, and the charges are balanced. And then to balance the 8 oxygens and 8 hydrogens, you would need 4 waters. So you would have the OH listed as a product. You would have H2O listed as a reactant. If you could balance that, that would be extra credit, not regular credit. Extra credit, not expecting you to balance that. But if you did balance it, you would get extra credit. And so then you can check your hydrogens, 8 from water, 8 from the OH minuses. You check your oxygens, 8 from the OH minuses, 4 from water, 4 from the MnO4 minus. And you would say that 5 electrons gained equal to 5 electrons lost. And so that also, for a problem like this, that would be extra credit. You would see that you had 5 electrons gained and 5 electrons lost. Balancing it, extra credit. Getting the oxidation numbers, labeling oxidation, half reaction, reduction, half reaction, oxidizing agent, reducing agent, that is regular credit. All right, next one. All right, next one, there's a guarantee that this one is on the test as well, and it is empirical and molecular formula. Always at least one empirical molecular formula problem on the test. All right, and so this one is 65.4% carbon, 5.5% hydrogen, and 29.1% oxygen. All right, one of those would not have to be given. And to find it, you know that when you are doing a percentages of atoms in a compound, it has to give you 100%. So if they said this is how much carbon and this is how much hydrogen and the remaining percent is oxygen, well, then you simply subtract from 100 and get 29.1. All right, molar mass has to be given if they ask for molecular formula. And so in this case, the molar mass is given as 220 grams per mole. All right, so when you're doing this empirical molecular formula, so calculate empirical formula and molecular formula. All right, so step one, you can assume any size sample you want. The easiest one is a 100-gram sample. All percentages are by mass. Unless otherwise stated, every percentage is by mass. So if you have a 100-gram sample, you got 65.4 grams of carbon. Convert that to moles, 12.01 grams per mole. All right, you got 5.5 grams of hydrogen in this 100-gram sample. Divide that by 1.01 grams per mole. This is your carbon, this is your hydrogen, and then a 100-gram sample, you have 29.1 grams of oxygen, and the molar mass, 16.00 grams per mole O. So when you push the buttons, you have your 65.4 divided by 12.01, and that gives you a 3 sig figs 5.45. You take your 5.5, divide by 1.01, 2 sig figs, 5.4. You take your 29.1, divided by 16.00, 1.82. All right, so whenever you have this problem, 100-gram sample, everything is grams. Convert it to moles by dividing by the atomic mass. And so now you have your moles of carbon, moles hydrogen, moles oxygen. And now the next step is to divide by the smallest number of moles, which is 1.82 is the smallest number of these three. 1.82, 1.82, 1.82. So now we know we have 1 mole O. And then when we take our 5.45 and divide by 1.82, we get 3. And so this is 3 moles carbon. This is 3 moles hydrogen. And so that is our empirical formula. It is a C3H3O. All right, so that is the empirical formula. All right, now we have to find the molecular formula. In order to do that, we need the molar mass. So we take the molar mass, which has to be given, and divide by the empirical mass, which we calculate. And that's going to equal an integer. So we were given 220 grams per mole. Now we have our empirical formula. We got to calculate the empirical mass. 3 times 12.01 plus 3 times 1.01 plus 16.00. All right, so you got 6, 3, 39, 16, 55. So you got 55.06 grams per mole. And the N is an integer. If this is not an integer, you did it wrong. If these moles aren't integers, then you got to make them integers by multiplying each one of them by a 2 or 3 or 4 or 5. All right, so when you take your 220 and you divide by 55.06, you get 4. All right, and so the molecular formula is C12H12O4. This is your molecular formula. This is your empirical formula. Empirical formula is lowest whole numbers, all right, versus your molecular formula, which is actually how many of each atom are in the molecule. So make sure you can do empirical molecular formula always on the test. All right. Number 8, we're doing a complete combustion. Complete combustion, you give CO2 and water. So C6 H12O6, which is glucose, and we burn glucose, and we get CO2 and water. All right, and so to balance this, we balance the carbon first. There's 6 of them here. We put a 6 here. Hydrogen next. There's 12 here. We put a 6 here. And then we finally do our oxygen. Do not forget the 6 oxygens here, which a lot of people forget, and they only use this one. There's oxygen in both of them. This one has 6. All right, so on this side, we have 12 plus 6. So on this side, we need 12 plus 6. And so we need that exact. We need 18 oxygens on this side, and we need 18 oxygens on that side. All right, so there are the coefficients required for the complete combustion of glucose. All right, so after we balance it, the question is how many grams of oxygen are required to burn 20 grams of glucose? All right, so we need to know how many grams of oxygen required to burn 20 grams of glucose. All right, so you always work in moles. The reason why you have a balanced chemical reaction. 1 mole of glucose reacts with 6 moles of oxygen gas to produce 6 moles of carbon dioxide and 6 moles of water. So to use this balanced chemical reaction, we have to work in moles. And so you take your 20 grams of glucose and convert it to moles. All right, so you got 6 times 12.01, you got 12 times 1.01, and you got 6 times 16. I'm not going to do that manually, so you got 6 carbons, 12 hydrogens, and 6 oxygens. 180.18. grams per mole of glucose. All right, and so it asks for grams of oxygen. And so this is the mole ratio that we need. The mole ratio, so this is the molar mass of C6H12O6. And so we know that 1 mole of C6H12O6 react with 6 moles of oxygen. So the moles of glucose cancel the moles of glucose. It didn't ask for how many moles of oxygen, it asked for how many grams. And note, this is O2, this is O2, this is 32.00 grams of O2 per mole of O2. All right, when it's O2, it is 32. When you're doing empirical formula, you want the moles of O. If you want the moles of O, it is 16. If you want the moles of O2, it is 32. All right, so now we're going to push those buttons. 20.0 divided by 180.18 times 6 times 32. And so you get 21.3 grams. So 21.3 grams of oxygen is required to burn 20 grams of glucose. And it's a very similar number because you see that the mole ratio is 6:1, but the molar mass is about 6 times larger for your glucose than your oxygen. All right, number 9. Number 9, again, there will definitely be a number of molecular, ionic, and net ionic equations. All right, and then it asks for the driving force and label the strong and weak electrolytes. So this is a lot of points on the test. CuCl2 plus NH3, NH4 sub 3, NH4 sub 3, PO4. All right, so we're doing a double replacement reaction. That means that the positive ion on this one is now going with the negative ion on this one. And the positive ion on this one is going with the negative ion on that one. And it doesn't matter what order you put them in. All right, so you're going to get ammonium chloride, and you're going to get copper 2 phosphate. All right, so this is your copper 2 and phosphate. So this is a +2, that's copper. Phosphate is -3. The least common multiple is 6. So we need Cu3PO4 sub 2. All right, and then to balance it, we have 3 coppers over there. We need 3 coppers over here. We have 3 ammoniums on the left. We need 3 ammoniums on the right. We have 6. We have 2. What am I doing here? All right. That would be phosphates. Yes, I skipped that. 2 phosphates. So let's do the phosphates next. We need 6 here. Sorry. All right. So you don't want to go to the ammoniums next. You want to go to the phosphates. All right. So phosphates, there's 2. So once you change it to 2 phosphates, you have 6 ammoniums. All right. All right. So we have our balanced chemical reaction. Now you have to know all your solubility rules. All right, and so this one is solubility rule with the halogens. All halides are soluble except for silver, mercury, and lead. That means this is a strong electrolyte. It is soluble. When it is soluble, that equals a strong electrolyte. All ammoniums are soluble. That means this one is soluble. This is a strong electrolyte. Ammonium chloride, all ammoniums are soluble. Right, so that is soluble. That means strong electrolyte. Copper 2 phosphate. Phosphates are insoluble unless you are lithium, a sodium, potassium, or ammonium salt. This is a copper phosphate. This is insoluble. All right, so when you are insoluble, you are a weak electrolyte, and you put solid there. All right, so now you have to be able to break these up. You got your 3 Cu plus 2s, you got your 6 Cl minuses, you've got your 6 NH4 pluses, you've got your 2 PO4 minus 3s, you've got your 6 NH4 pluses on the right, you got your 6 Cl minuses on the right, and then so your strong electrolytes break up into ions. Your weak electrolytes, the insoluble salts, stay together and they are solid. So all solids, liquids, and gases stay together. So Cu3PO4 sub 2, and that is a solid. All right, so that is the ionic. So you have your molecular, where everything is a neutral molecule, molecular. Then you have your ionic. Anything that's a strong electrolyte has to be broken into its ions. And then you have the net ionic. All right, so you can't be both a reactant and a product. So if you have your Cl minus, you can't have Cl minus be a reactant and a product. It is a reactant or a product, or it cancels out completely. You subtract 6 Cl minuses from both sides. It is actually not in the net ionic. Same with the ammoniums. You subtract 6 ammoniums from both sides. And so what you are left with is 3 Cu plus 2s plus 2 PO4 minus 3s, yielding Cu3PO4 sub 2 solid. All right, and the things that are gone completely and they do not show up in the net ionic, those are called spectator ions. So your spectator ions in this problem are the chloride ion, Cl minus, and your ammonium ion, NH4 plus. You do not have to put the 6 in front of the number. If you do, I don't care, but you just need to say what the spectator ions are. That is the Cl minus ion and the NH4 plus ion. All right, anytime you form a solid, the driving force is formation of a precipitate. Anytime you're forming a solid, that's called a formation of a precipitate. All right, so that would be an example of the driving force formation of a precipitate. There will, almost every one of these tests has at least one precipitate, driving force, formation of precipitate. All right, part B, HClO4 reacts with sodium carbonate. All right, so this one, again, this one is a special case, one that you have to memorize. It's hard to remember in a test. You will get partial credit if you just do the double replacement and don't remember. But to get full credit, you have to remember that an acid with a carbonate is going to give you CO2 and water. All right, and so you're going to get sodium perchlorate, so you got your NaClO4, but you do not get H2CO3. When you have a carbonate with an acid, you get CO2 and water, plus CO2 gas and H2O liquid. All right, so to balance this, you have 2 sodiums here, you need 2 sodiums there. You have 2 perchlorates, you need 2 perchlorates. And we have 2 hydrogens, 1 carbon, 3 oxygens. Everything now is balanced. So this is your molecular. All right, so now you got to determine if it's a strong electrolyte or a weak electrolyte. So this is one of the 6 strong acids. Make sure you have your 6 strong acids memorized. So this is a strong acid, one of the 6 that you must have memorized. So therefore, it is a strong electrolyte. All sodiums are soluble. This is soluble. And so it's a strong electrolyte. All sodiums are soluble. Therefore, it is a strong electrolyte. All right. So your molecular compounds, your non-ionic compounds, molecular compounds, these are all non-electrolytes. These are all non-electrolytes. All right. So your strong electrolyte, we break it up. So we get 2H plus, we get 2 ClO4 minus. All sodiums are soluble, break it up, strong electrolyte, 2 Na plus, and CO3 minus 2. All sodiums are soluble, break it up, 2 Na plus, and 2 ClO4 minus. All solids, liquids, and gases stay together, plus CO2 gas, plus H2O liquid. All right, so now you see that you have on both sides, you have so this is called the ionic. All right, so the net ionic, we see if we have exactly the same thing on both sides, that can cancel out. And we do. We have 2 Na plus that can be subtracted from both sides. So get rid of your 2 Na pluses. Your 2 ClO4 minuses also are on both sides, and they are gone. So the net ionic is 2H plus and CO3 minus 2, yielding CO2 and H2O. All right, CO2 is a gas, H2O is a liquid. All right, and so the driving force of this one is formation of a gas. All right, so there are 3 of those that you have, sort of 4. So carbonate or bicarbonate would work the same way. And then your sulfite, I guess the bisulfite would work the same way too, but bicarbonate is very common. So your sulfite and your sulfide, your H2S gas, those are the 3 formations of a gas that you will need to know. So your spectator ions, those are the Na plus and the ClO4 minus. Again, if you put 2 in front of those, I don't care. But I just want to give the ions that do not show up in the net ionic. There may be some, there may be none. All right, part C. Part C is HC2H3O2. We got acetic acid. We've got copper 2 oxide. All right, we're going to do a double replacement reaction. And so copper 2 is going to go with the acetate. So we have Cu and then C2H3O2 sub 2. And then the H goes with the O, and that gives you H2O. And so to balance that, we have a 2 in front of our acetic acid. So that's your molecular. All right, so ionic. We have to, in order to get to the ionic, we have to label things as strong, weak, or non-electrophiles. All right, so all acids are aqueous. All right, and so you would put aqueous here. And then your copper oxide. I would have to tell you that copper oxide is a solid. So I wrote this problem. I gave you the first two. And on this one, I'm going to put solid there for my copper oxide. All right, and so, but your acetates, all acetates are soluble. All right, so this first acid here, acetic acid, is not one of the 6 strong acids. So this is a weak acid. All right, which makes it a weak electrophile. This is insoluble. All right, so if I ask if it's soluble or not, and I wrote solid here, that's the answer. The answer is it is insoluble. It's not on your chart. That's why on all the rest of them, there is nothing written. On this one, I put solid for copper oxide. That is telling you that that is insoluble. And that makes it a weak electrolyte. All right, all acetates are soluble except for acetic acid. So this is soluble. All right, and so this is a strong electrolyte. And of course, water is a liquid. This is a non-electrolyte. All right, so you do not break up your weak electrolytes, so your acetic acid stays together. So you have 2HC2H3O2 aqueous. And you've got your C, we didn't balance it, did we? Yeah, we did. Okay, then we have our CuO, solid. Weak electrolyte stays together. And now we have our strong electrolyte, which breaks up into Cu plus 2 and 2 C2H3O2 minuses plus H2O liquid. All right, and then this is a case where you do not have any spectator ions. We do not have anything identical on both sides. So this is both the ionic and net ionic. And you only have ionic and net ionic be the same if there are no spectator ions. And your molecular ionic and net ionic could all be the same if you had no soluble compounds in the whole equation. You could also have a net ionic where everything cancels, and then that is a no reaction. All right, so now the driving force of this, when you are forming water liquid, unless it comes with a gas, when you are forming water liquid and you had an acid, this is a neutralization. So if you are forming water and there's no gases here, if it's forming a gas, it is going to be formation of a gas. If it is forming a solid, it is going to be a formation of a precipitate. If you do not have a solid or a gas produced, but water is produced, then you have a neutralization reaction. All right, then part D. That one is H2C3H2O4 plus AlOH3. All right, so this one is a diprotic acid. All right, so those two hydrogens are both acidic. All right, and so you have this acid here. We know it's an acid because it starts with H. We know it's a weak acid because it's not one of the 6 memorized strong acid. So this is a weak acid, which makes it a weak electrolyte. All right, and then and so again, all acids are aqueous, so we put aqueous here. The hydroxides, all right, so you have your 6 strong bases. This is not one of them. This is a weak base. We have 6 strong acids and 6 strong bases. This is a weak base, not one of the hydroxides that is a strong base. That makes it a weak electrophile, and this is not an acid, and so you put solid here. The only time you would have a weak electrolyte to be aqueous, that is your weak acids. Anything else that's a weak electrolyte is going to be a solid. All right, so now the aluminum is going to go with the C3H2O4, but you have to see that this is 2 H pluses. All right, it's not going to break up, but you need to see that that's 2 H pluses, which means that this is C3H2O4 minus 2. So when you do the double replacement, H plus is going with OH. That's going to give you your water. Your C3H2O4 minus 2 is going to go with the Al plus 3. This is in the plus 3 column, and you also know that the OH is minus 1. And so when you're doing your double replacement, you have to make neutral molecules. All molecules are neutral. All right, and so the minus 2 here and the plus 3 for the aluminum, the least common multiple is 6. And so you need Al2, then you need parentheses C3H2O4 sub 3. And this would also be a bad question. This would not be one that's on the test, or I would have to give you some information here. And I'm going to say that the aluminum product is insoluble. I would have to tell you that. This is not on the memorized chart. I would say this is insoluble. Oh, that would be a bad question. All right, so I will say that this is soluble. That's what I would say on the test. I would not say that's insoluble because then that would be 2 correct answers. Okay. That one is soluble. All right, so we have to balance it. All right, and so you have 2 aluminums, you need 2 aluminums. You have 3 of your minus 2s, you need 3 of your C3H2O4 minus 2s. And now we have 6 H's and 6 OH's, which means we have 6 H2O's. All right, so that's soluble. I will have to tell you that. So I could pick whichever one I want, whatever one, because that is not to be memorized. All right, soluble. So that means that this is a strong electrolyte. I will either tell you that the product is soluble, or I will tell you that the product is a strong electrolyte. Either way, it's the same thing. If you're soluble, you're a strong electrolyte. If you're a strong electrolyte, you're soluble. All right, so when we do our net ionic, we keep weak acids together, 3H2C3H2O4. Aqueous stays together. Our 2AlOH sub 3 stays together. It is a solid. 6 H2O liquids. Oh, this is a non-electrolyte again. Anytime you have water, it's a non-electrolyte liquid. And then I said this one's soluble, so we're going to break it up. And we get 2 Al plus 3s. And we get 3 of the C3H2O4 minus 2s. All right, so this one, just like a previous one, there is no ions that are going to cancel on both sides. And so your net ionic, okay, I guess whatever. So this is the ionic and net ionic, and the net ionic. So there are no ions, actually there's 0 ions on the left side, so you can't have any ions canceling. And so again, no spectator ions. All right, and so this one, again, this one is the classic acid and the classic base. giving you a salt. Any ionic compound is a salt, and water. So again, this one is neutralization. So anytime you have an acid, so a compound that starts with H, and you have a base, any compound that has hydroxide, that is going to be a neutralization reaction. That is the driving force for part D. All right, but yeah, you would not know the product, so the product answer for soluble or insoluble has to be given. Part E. All right, so here we have NH4 sub 2 SO4, so ammonium sulfate with potassium chloride. All right, we do our double replacement reaction. So our NH4 is going to go with our Cl. NH4 goes with Cl, NH4Cl. And the potassium goes with the sulfate, K2SO4. All right, and so then to balance it, we have 2 potassiums, we need 2 potassiums. We have 2 ammoniums, we need 2 ammoniums. We have 1 sulfate, 2 chlorides, 2 chlorides. So we have a balanced molecular reaction. All right, so now we have to use our solubility rules. All ammoniums are soluble. This one is soluble, equals strong electrolyte. All potassiums are soluble. This is soluble, equals strong electrolyte. All ammoniums are soluble. Soluble equals strong electrolyte. All potassiums are soluble. This one is soluble. This is a strong electrolyte. So all of these are strong electrolytes. All of these are potassium and ammonium salts, and all of those are soluble. The only exception would be an ammonium hydroxide. All right, so when you go to the ionic, you got to break them all up. 2 NH4 plus and SO4 minus 2. 2 K plus. 2 Cl minus. 2 NH4 plus. 2 Cl minus. 2 K plus. SO4 minus 2. So when everything is a strong electrolyte, you break everything up, and now everything cancels. And so the net ionic is no reaction. All right, so there's nothing that occurs when you mix those things together. No reaction at all, because when you cancel all your common ions, that's the subtract 2 ammonium, subtract 1 sulfate from both sides, 2 potassiums, 2 chlorines. You see that you have nothing left. This is no reaction. All right, and so the spectator ions, well, they're all spectator ions. So that is NH4 plus, that is SO4 minus 2, and that is K plus, and that is Cl minus. All of the ions are spectator ions. There is no reaction here. All right, so if everything is a strong electrolyte, then you have no reaction. All right, then the last question is calculate the density. 10. Calculate the density of 12 molar HCl that is 36% HCl. All right. So anytime you have a percent, you can assume a 100-gram sample. But this is HCl, hydrochloric acid, 12 molar. Hydrochloric acid, concentrated hydrochloric acid, is 36% hydrochloric acid. All right. So if you assume a 100-gram sample, that means that you have 36.0 grams of HCl. and all acids are aqueous, moles per liter of solution. All right, and so the other 64.0 grams would be water. All right, and then that would give us 100 grams of solution. All right, and of course you have 12.0 moles of HCl, that's the moles of the solute, per liter of solution. All right, so that is the information that this gives us. Now, you need to know what the units of density are. Density is mass over volume, but that is not good enough. If you just say mass over volume, you've got three masses. You only have the one volume, but you have three masses. So you need to know that when you are doing density, it is the mass. When you did the density of your unknown, that unknown could have been salt water, that unknown could have been anything, and your unknown was not a pure compound, it was a mixture. And so we took the mass of that mixture, that is the mass of solution, and we then looked at it and took the volume. We read the graduated cylinder, so this is the volume of that solution. So when we want the density, we want the mass of the solution. Well, we got that. It's right here. The mass of the solution is 100 grams. We now need the volume of solution. The only place we have volume of solution is right here. And so we have to get our molarity to give us volume of solution. All right, but we do have this. We have, with our 100-gram sample, we know that we have 36 grams of HCl. So you take your 36.0 grams of HCl and you convert that into moles. So you look at the periodic table, you've got your H, 1.01, you've got your chlorine, 35.45, and so this is 36.46 as a molar mass. So you have 36.46 grams of HCl per mole of HCl. And now you have your molarity, which is right here, which tells us that for 1 liter of this solution, we have 12.0 moles of HCl. And so moles of HCl cancel moles of HCl, grams of HCl cancel grams of HCl, and now we have liters of solution, but we want the density of a liquid. All right, so when you do density of a liquid, we want grams per milliliter, not grams per liter. So we want to convert this liters into milliliters. And so we know that 1 liter is 1,000 milliliters. All right, and so then the liters cancel the liters, and you have your answer. So you have your 36 divided by 36.46 divided by 12 times 1,000. All right, and you get 82.3 milliliters. All right, so now what we needed was the density. The density is equal to the mass of solution divided by the volume of solution. This is a liquid, so we wanted the mass to be in grams, we wanted the volume to be in milliliters, and that's what we have. So now we can calculate our density. Mass of solution, 100 grams. Volume of solution, 82.3 mils. And so when you take your 100 and divide by 82.3, you get 1.22 grams per milliliter. All right, so this is a very difficult question. You have to use the definition of percent, parts per hundred. It is a mass percent. Assume 100-gram sample. Then you have your mass of your HCl and the mass of the water and the mass of solution. So you have to know solute, solvent, solution. All right, then you also have to know molarity. What does that mean? You have 12 moles of HCl per liter of solution. All right, and then you also have to know density is the mass of solution divided by volume of solution. So there's a lot of things to know for this problem. That is the end of the study guide for exam 2.